Good morning, everyone, and welcome to today's lecture. This is lecture number 7 or 6. We are just a minute. According to me, it's lecture number 7 or 6. Anyways, we are dealing with kinetic theory of gases, and in the previous class, we had seen the important points about this kinetic theory of gases. What all points had we seen? We go back. We had seen the various types of speeds of gases, the RMS speed, the most probable speed, the average speed. We had also seen Maxwell's distribution of speeds, and we had seen that this VRMS is greater than V average is greater than V most probable. The most probable speed is the highest. Do we understand this, everyone?
Yes, sir.
Okay. Then we had seen what happens when the temperature is raised. We have seen that the speed of the molecules increase. VRMS or V most probable is directly proportional to root over T and inversely proportional to root over the molecular mass. Does not depend on pressure. We'd also seen kinetic energy of gas molecules, different types, different ways in which you have written total energy per unit volume, average energy per unit mole, average energy per unit molecule, 3 by 2 kT, 3 by 2 RT, and so on. You all remember this? Yes or no? It also
Yes, sir.
seen this question where we had found out the pressure exerted by one gas molecule by a number of gas molecules. We found out the change in momentum of one molecule and we multiplied it by the number of molecules that were striking. Okay, having said that, now is the time that we move ahead and solve some more questions based on your kinetic theory of gases. Remember, I'm suspecting a question may come from here, so we will solve all types of questions so that we get confident. This is the first question that comes into the picture. The root mean square speed of a hydrogen molecule of an ideal hydrogen gas kept in a gas chamber at 0 degrees Celsius is 3180 meter per second. What is the pressure of hydrogen? Density is given and 1 atmospheric pressure. How much it is? That is also given. It's just a matter of calculation. I'll give you 1 minute. Let me know what is the answer. So how do we do this? Just have to remember the formula. P is equal to 1 by 3 rho V RMS square. Do we remember this formula? Yes or no?
Yes, sir.
That's it. You just put the values and get your answers. Nothing else. Pressure is 1 by 3. Rho is given as 8.99 into 10 raised to the power minus 2. This 8.99, you can take it as 3. Now you can take it as 9. Just have to simplify your calculation. Into VRMS square 3180 square. This 3180, you can take it as 3000 also, just to get your answers quickly. Do you understand what I'm saying?
Yes, sir.
So once you get it, you will get something around 2.8, 2.9 atmosphere, because one atmosphere is given as this much. You will get something around 3.03, and that is your answer, 3 atmospheres. So remember this formula. Everyone got this?
Yes, sir.
Okay, this one, the next one. Shall we move on to the next one? Yes or no?
Yes, sir.
This is the next one. Similar question, and I hope you can give me the answer. A cylinder of capacity 20 liters is filled with hydrogen gas. Volume of the cylinder is given. The total average kinetic energy. What do you mean by total average kinetic energy? You just think about the total kinetic energy of the translatory motion of its molecules is 1.5 into 10 raised to the power 5 joules. What is the pressure of hydrogen in the cylinder? Remember this term, translatory motion. We will come to know translatory. We have already done translation and rotation. In gas molecules, what is translation and rotation? Don't worry, it is coming up in this class only. Right now, I have given you the formula of kinetic energy. That is the formula that you have to apply. I'll give you 2 minutes to give me the answer for this one. Option D is correct. Well done. Total kinetic energy, you can write it as half m total mass into VRMS square. Total pressure, you can write so total kinetic energy, you can write half, and total pressure, you can write half rho into VRMS square. From there, actually, you can find out this relation, and it is very simple. The total pressure will be 2 by 3 times the total kinetic energy per unit volume. You just have to put the result, get your answer, and stay happy. I hope you have got this. Everyone, this is the answer that we are looking at. Well done. Shall we move on to the next question? We understand this? Shall we move on to the next question?
Sir.
This one is the next one in line. N molecules each of mass m of gas A and 2 N molecules each of mass 2m of gas B are contained in the same vessel at temperature T. The mean square of velocity, remember, it is not RMS velocity, it is the square of it. That is known as mean square velocity, not root mean square. Root mean square is VRMS. VRMS square is mean square velocity. The mean square velocity of molecules of gas B is V square, and the mean square of X component, X component, X component of velocity of molecules of gas A is W square. What is the ratio of W2 square by V2 square? I'll give you 2 minutes to get me this answer. So, gas A, the mass of each molecule is m. So, if I call the X component of its mean square velocity as omega naught, is VRMS square for the gas A will be 3 times W square. Do we understand this? Because the x component is given, and I told you the x, y, and z component of square of RMS velocity, mean square velocity are equal, and that is equal to v square RMS by 3. Yes or no?
Yes, sir.
Similarly, v RMS square of b is v square. This is equal to 3 kt by m. This is equal to 3 kt by 2m. So from here, we can easily find out w square by v square, and I think you will get the result as 2 by 3. Do we understand how this is done?
Yes, sir.
Was it so difficult that you could not do it? What was so difficult in this question? It was a straightforward, simple question. Note it down as we move on to the next question. Shall we move on to the next question?
Yes, sir.
This is the next question. At room temperature, the RMS speed of molecules of a certain diatomic gas is found to be 1930 meter per second. Which gas is that? Simple, straightforward question this is. I'll give you 2 minutes to give me the answer. The straightforward question. VRMS is root over 3 RT by M naught. From here, you can find out the value of M naught. At room temperature, it is given. Remember, room temperature is taken as 300 Kelvin. That is the only thing you had to remember. So M naught becomes how much? 3 RT by VRMS square. Do we understand this? If you solve this, I think you are going to get 2 grams. Since it is 2 grams, the gas would be hydrogen. Anyone got this answer? Yes or no?
No, sir.
Why no, sir? Why no, sir? Any specific reason, sir? Or we don't remember the formula, sir? Chalo, next one. And I hope you can give me this one. Do it fast. We have to complete this KTG today. And we have to do a certain number of questions, and we have to do a certain portion that I think I included in KTG. Two gases, A and B, given this, where T and M is the temperature and the mass. CA and CB are the RMS speed. What is the ratio of CA and CB? Do it fast. A is correct. Again, you must remember, you just have to apply the formula VRMS is equal to 3RT by M naught. So speed of A, RMS speed of A divided by RMS speed of B will be equal to TA by MA multiplied by MB by TB. And you can see that it is coming as 4. Root of that will be 2. So the answer happens to be 2. Do we understand this? Yes or no? No, yes.
Yes, sir.
Next question. Straightforward question. The RMS speed of molecules of a gas in a vessel is 400 meter per second. If half of the gas leaks out at constant temperature, What is the RMS speed of the remaining molecules? What is the answer for this one? What is the answer to this one? You don't have to calculate because you cannot calculate anything here. The answer is same. The RMS speed of gas molecules does not depend on the number of molecules which are present. You look at the formula and I have given it so many times. It only depends on root over 3 RT by M. It depends on temperature and it depends on the molecular mass of the gas. Gas escaping out does not change the molecular mass of the gas and therefore the answer remains same. The speed remains same. Do we understand this?
Yes, sir.
Yes or no? Comes the next question. The RMS speed of hydrogen molecules at 300 Kelvin, we have found it out, is 1930 meter per second. Then the root mean square speed, RMS speed of oxygen molecules at 900 Kelvin is how much? Give you 1 minute to do this. The RMS velocity of any gas molecule is 3 RT by molecular mass of the gas. So it is directly proportional to T and inversely proportional to M naught. We have to find the RMS velocity of oxygen at 900 Kelvin. This divided by velocity of hydrogen at 300 Kelvin. The ratio will be temperature of oxygen, which is 900 Kelvin, divided by the molecular mass. Yes, beta?
Yes, sir.
Divided by the molecular mass of oxygen, which is 32, multiplied by the molecular mass of hydrogen, which is 2, divided by the temperature of hydrogen, which is 300. From here, what you will get? You will get root over 3 by 4. The speed of oxygen molecules is root over 3 by 4 multiplied by 1930, and the answer you will get will be somewhere around 836 meter per second. Is it so tough that you cannot do better? Is it tough? What you could not do here? Tell me. What was the problem?
Calculation mistakes, sir.
Calculate, nothing to calculate here, beta. You cannot do calculation mistake in question of this nature. No, it is not accepted. Can't accept it. Anyways, students are like cash vouchers. Sometimes the cash voucher may not work. You can also redeem. You can always redeem that cash voucher again. This is the next question in which you can redeem yourself. At what temperature is the root mean square of hydrogen molecule is equal to that of oxygen molecule at 47 degrees Celsius? Similar question put in a different way. I'll give you time to redeem yourself. Option A is correct. So again, every time I write this formula so that you see it so many times so that you can remember it. Now RMS speed of Hydrogen should be equal to the RMS speed of oxygen. So temperature of oxygen divided by molecular mass of oxygen should be equal to temperature of hydrogen divided by molecular mass of hydrogen. Everything is known. Remember, all the things should be in Kelvin and not degree Celsius. You do degree Celsius, everything gets distorted, and the answer that you are going to get will be 20 Kelvin. Very low temperature it is. Next question, which should not require any calculation, which should be a straight away yes or a no. Yes or a no, no or a yes. The answer for this one, a lorry. A cooking gas containers are kept in a lorry moving with a uniform speed. The temperature of the gas molecules inside will increase, decrease, remain same, decrease for some while increase for others. I love this option. Yes. What will happen to the temperature of the gas molecule?
Remains, remains same, sir.
It will remain same. If it is moving with a uniform speed, there is no force acting on it. So the RMS speed remains same. If the RMS speed remains same, that means the temperature will remain same. Do we understand this, or this has gone above our head saying bye bye?
Yes, sir. Understood.
This is the next one, my dear friends. This just checks whether you know the formula of RMS speed. The speed of five molecules of a gas in arbitrary units are given as this. What is the root mean square speed? You should also find out the average speed. Let me okay. 2 minutes you have to give me the answer. Option A, sir, is I don't know. How did you get that option, sir? But that is absolutely wrong, sir.
Option D, sir.
Option D, sir, is absolutely right, sir. 4.24, sir. You have to find out the RMS speed. Did not give you the formula of RMS speed. Now is the time that you can write the formula of RMS speed. RMS speed will be nothing but summation of VI square divided by the number of molecules n. Do we understand this? Huh?
Yes, sir. Yes, sir.
Uh, We can just now put the formula 2 square plus 3 square plus 4 square plus 5 square plus 6 square. How many molecules are there? There are only 8. 5 molecules. And you will get your answer, I think, as 4.24. Yes or no?
Yes, sir.
If we have to find out the average speed would have been 2 plus 3 plus 4 plus 5 plus 6 divided by 5. Do we understand this?
Yes, sir.
If we had to find out the most probable speed, we had to find out which speed is possessed by maximum number of molecules. As you can see, all molecules possess different speed. If we had one more molecule which had a speed of 2 meter per second, the most probable speed becomes 2. Do we understand this?
Yes, sir.
If we had one molecule more which had a speed of 3 meter per second, then the most probable speed becomes 3 meter per second and so on. Most probable speed is the speed with which maximum number of molecules have. Do we understand this, or this has gone above our head saying bye bye?
Understood, sir.
This question has been repeated multiple number of times and it comes on your screen now. Let me have the solution and the answer for this. The question comes. 2 minutes you have to show me your talent. I have the answer. Pressure remaining same, eh? Pressure is half rho VRMS squared. Rho is the density. You can write it as half mass of one molecule multiplied by number of molecules divided by V into VRMS squared. Do you understand what we are going to get?
Yes, sir.
What, sir? So pressure is directly proportional to mass of one molecule into VRMS squared. Now, if you double the speed of each molecule, the RMS speed will be doubled, yes or no? So, P divided by P naught, the original pressure, the mass is half m by 2 multiplied by velocity is doubled. Original velocity is v. It becomes 4v divided by m into v, and the answer is 2p naught. 2p naught is the answer. What did you get? 2 times p naught is the answer. Do we understand this? Yes or no? No, yes. This is a question from JEE. Multiple option correct. So you have more than one option correct. Question comes on your screen right now. You have 2 minutes to show me your talents. This question is multiple option correct, sir. So which are the correct options, sir? No molecule can have speed greater than RMS speed or root 2 RMS speed. Is it correct or wrong?
Wrong, sir.
No molecule can have speed less than V, most probable by root 2. Correct or wrong? Wrong.
Wrong, sir.
VMP is less than V average is less than VRMS. Correct or not?
అది
Huh?
కూడా
Correct. I've given
correct.
you so many times.
Correct.
The average kinetic energy of a molecule, that is average kinetic energy per molecule. Average kinetic energy per molecule is uh, average kinetic energy per molecule kT by n is half m into VRMS square. Yes or no? And you know the relation between VRMS and V
Sir,
probable. Yes or no?
sir, RMS speed is less than all the speeds, no, sir.
Huh?
Okay, sir.
We are in this universe. This is a good universe to live in. You know this, na? This is a good universe. Or we have forgotten this universe. We have forgotten everything. Gave you everything in everything. I gave you everything and everything here in Maxwell's law as well. Everything and everything. Can't forget this. A simple mistake and your IIT-JEE ka sapna is gone. Shameful act. Shameful act. Okay, so when you put the value of RMS in terms of most probable, you will get the average kinetic energy per molecule as 3 by 4 m into V most probable squared. Therefore, option number 3 and option number 4 are correct, my dear friends. Do we understand this? Oh, this has gone above our head saying bye-bye.
Understood, sir.
Next question, sir. This one, sir, I'll give you 2 minutes to solve this question, sir. Option C, sir. 2V, sir. Is that so, sir? That is correct, sir. So, again, sir, VRMS is root over 3RT by M, not. Temperature is doubled. So it becomes 2T. Molecules dissociate into atoms. So the molecular mass becomes half. Do we understand this? Huh? Yes or no? So it becomes M by
Yes,
2.
sir.
So 2 into 2 becomes 4. 4 ka root becomes 2. And the answer is 2. This one, my dear friends. Which of the following statements is true? Absolute 0 degree temperature is not zero energy temperature. Two different gas at the same temperature and same pressure have equal RMS. The RMS speed of molecules of different ideal gas maintained at the same temperature are the same. Given sample of 1 cc of hydrogen and 1 cc of hydrogen, both in NTP, the oxygen sample has a large number of molecules. Only one option is correct here. Huh?
Option A, sir.
Well done. Option is that is correct, sir. The other three options are correct, are false. The only correct option is option A. Remember, at absolute zero, the kinetic energy of the gas molecules becomes zero, but the gas molecules will have potential energy. It would be very less, but they would have potential energy. Therefore, the zero energy, absolute zero of temperature, energy is not zero. It's only the kinetic energy of the gas molecules is zero. Do we understand this, or this has gone above our head saying bye bye?
We understood, sir.
Next one is this, sir. Give me the answer fast, sir. A vessel is partitioned into two equal halves by a fixed diathermic separator. Diathermic means it can allow heat to flow. Two different ideal gases are filled in the left and the right half. The RMS speed of the molecule in the left half is equal to the RMS speed, mean speed, mean speed of molecule in the R part. What is the ratio of the mass of a molecule in L part to that of a molecule in R part? Yes, my dear friends. Option D is correct. The RMS speed of gas in the left part will be 3 RT by mass of the gas root over. This is equal to the mean speed. Mean speed is 8 by pi RT by MR. From here, if you equate both, you will get this answer. Yes or no? No or yes?
Yes, sir.
Everyone got this?
Yes.
Well done. This one, my dear friends. Read the given statement and decide which are correct based on the basis of kinetic theory of gases. I'll give you a minute to think about it and give me the answer. So, which one is the correct option? Option number 1, energy of a molecule at absolute temperature is 0. False or true or false?
False, sir.
False. I told you that they have potential energy. RMS speed of different gases at the same temperature are same. True or false?
False.
1 gram of an all ideal gas will have the same kinetic energy at the same temperature. True or false?
False, sir.
1 mole of all ideal gas will have same mean kinetic energy at the same temperature. Yes, true or false? This is the only statement that is true. Remember, I have given you average kinetic energy per mole. For 1 mole is 3 by 2 RT. Average kinetic energy per molecule is 3 by 2 KT. From average kinetic energy per mole, you can find out the average kinetic energy per gram. You divide it by the molecular mass, but then molecular mass will come and therefore kinetic energy per gram will not be same. Do we understand this?
Yes, sir.
Only per mole and per molecule it is same, not per gram of the gas. We understand this, or this has gone above our head saying bye bye.
We understood, sir.
But then I did not get an answer. Next one, I need an answer. A vessel contains a mixture of 1 mole of oxygen and 2 moles of nitrogen at 300 Kelvin. The ratio of average rotational kinetic energy, we have not done this, so I will I will change this question from average rotational to simply average kinetic energy. Right now, we don't know whether it is rotational or what. Average kinetic energy per O2 molecule and per N2 molecule. What is the answer for this one? I've just taken out the rotational part out from the picture. Yes. Huh?
1:2, sir.
1:2, sir. Per molecule. Per molecule. The answer is 1:1. Just now I told you, many times I have told you, per molecule is 3 by 2 kT. Per mole is 3 by 2 RT. It only depends on the temperature. It does not depend on the gas. Do we understand this? Or this has gone above our head saying bye bye.
We understood, sir.
Okay. As I told you, these questions might be a bit confusing. Per mole, per molecule, you have to read the question correctly and then give your answers. A gas mixture consists of molecules of type 1, 2, 3. molar mass, molecular mass, M1, M2, N3, VRMS and K average are RMS speed and average kinetic energy of the gas. Which of the following is true? Whenever someone says average kinetic energy, he is meaning average kinetic energy per mole or per molecule. It will be per molecule probably. Yes.
Option A, sir.
Option A, sir. Well done, sir. Do we understand this, sir? Next one, sir. This one, sir. This is IIT-JEE, the IIT that I gave. Two times IIT happened. One before the one because the paper was cancelled. This question came in the this question came in the re-exam. The average transitional kinetic energy and the RMS, no, the average transitional kinetic energy of O2 molecules at a particular temperature is 0.048 electron volt. The transitional kinetic energy of N2 molecule average, you are asking, at the same temperature is, and the answer is, eh?
Option C, sir.
Option C, sir. So now we have understood the concept. This question came from the original JEE paper of 1997, the JEE that I gave, which got cancelled. This paper was not cancelled, I probably would have been in the top 300 or 500. Anyways, the average transitional kinetic energy and the RMS speed of molecules in a sample of oxygen gas are 300 Kelvin and this. The corresponding values at 600 Kelvin and are nearly how much? You have 2 minutes to give me the answer.
Option D.
Rabash, good. The energy directly proportional to temperature, it becomes 2 times. RMS speed is root 2 times. So the only option that matches is this one. Well done. This one. 3 course vessels A, B, and C are at the same temperature and contain gases which obey the Maxwellian distribution of velocities. Don't get confused. Maxwell's curve we have seen. Vessel A contains O2, vessel B contains N2, and C a mixture of O2 and N2. The average speed, RMS speed, no, the average speed of O2 molecules is A is V1 and that of N2 molecules in vessel B is V2. The average speed of O2 molecules in vessel C is equal to how much? IIT-JEE 1992. And the answer is huh? No idea.
Option C, sir.
Option C, sir. V1, V2 ka root. I don't know in which universe you are living. It is V1. The RMS speed only depends on the average speed only depends on the temperature and the molecular mass of the gas. It does not depend on anything else. Whether you mix it or you don't mix it doesn't matter. Which cylinder it is put doesn't matter. Number of molecules doesn't matter. Do we understand this? Yes or no? No, yes. Huh?
Yes, sir.
Which graph represents the variation of mean kinetic energy, average kinetic energy of molecules with the temperature T degrees Celsius? Degree Celsius, my dear friends, degree Celsius. In degree Celsius. Anyone for degree Celsius?
Option C, sir.
Option C, sir, is the correct answer, sir. If this would have been versus capital T, that means absolute temperature, kinetic energy, then the answer would have been option A. Do we understand this? So this is gone above our thing. Bye bye.
Understood, sir.
Then we welcome ourselves to the next heading of this chapter. Degrees of freedom. How many degrees of freedom you have? Are you free? Do you have freedom? India is a democratic country. We are free. We have fundamental rights. What about the gas molecules? What do you mean by the term degrees of freedom? The term degrees of freedom, we can refer to it in many ways. The term degrees of freedom may refer to the number of possible independent motion a system or a gas molecule can have. This degrees of freedom is normally written by the small letter f. The number of different ways in which a molecule can process energy or can have independent motion is known as the degrees of freedom. So we can also write it in this way. The total number of independent modes in which a gas molecule can possess energy is known as its degrees of freedom. Do we understand this? Yes
Yes, sir.
or no? No, yes. Now
Yeah.
this independent motion that a molecule or a system can have can be of three types or a combination of this. There could be translational degree of freedom, there could be rotational degree of freedom, and there could be vibrational degree of freedom. Do we understand this? Degrees of freedom. Degrees of freedom, my dear friend. Degrees of freedom. Degrees of freedom. The number of possible ways in which a gas particles can have energy. You can also understand it in a different way. The number of independent coordinates that are required to specify the state of a system, how many coordinates are required? Degrees of freedom. I'll give you a minute to note it down. Since we have understood what are degrees of freedom, you can take simple examples and elaborate this point further. For example, if you have a body moving in one dimension, moving in a straight line, a body moving in a straight line, how many degrees of freedom it will have? If a body is moving in a straight line, how many degrees of freedom it will have? How many degrees of freedom it will have if a body is moving in a straight line? 1. Yes or no?
Yes, sir.
And that 1, because it only has one coordinate which is changing, it is moving along x-axis. One coordinate is changing. The first, listen to me, then I will give you time to write. Then, you understand what do you mean by degrees of freedom? Yes or no?
Yes, sir.
Then, if it is a projectile motion, if a body is moving in 2 dimension in a plane, the number of degrees of freedom it will have would be 2. Yes or no?
Yes, sir.
Then, if a body is moving in space, the body is moving in space. If a body is moving in space, it will have 3 degrees of freedom. Yes or no?
Yes, sir.
3 degrees of translational freedom. Let me add here. Yes or no?
Yes, sir.
Now, we take another example. If we have a rolling sphere, if we have a sphere which is rotating as well as translating, the number of degrees of freedom would be 2. One because of rotation, one because of rotational, and another because of translational. Do we understand this?
Yes, sir.
But remember, and this could be a trick question, in pure rolling, how many degrees of freedom it has?
1, sir.
In pure rolling, it only has 1 degree of freedom, because pure rolling can be treated as a pure rotation about the point. Okay,
Sir.
so pure rolling, we can specify its energy in terms of 1 coordinate, 1 factor, 1 velocity, and therefore it has 1 degree of freedom. Do we understand this?
Yes, sir.
Now, when we talk about, have you noted this down, everyone?
No, sir.
Okay, then I'll give you time to note it down. Let me know once you are done. So, let's move ahead. Now, remember, whenever we are talking about the translational degrees of freedom, they will be for a gas molecule, there would be all gas molecules, whether they are atoms, whether they are monatomic gas, whether they are diatomic gas, they will have 3 translational degrees of freedom, because they can move in all the 3 axes, x, y, and z axis. Do we understand this?
Yes, sir.
Now, as far as rotational degrees of freedom are concerned, depending on the structure of the gas molecule, the rotational degrees of freedom vary. It can be 0, it can be 2, or 3. So depending on the structure, and we will see, depending on the structure, the rotational degrees of freedom can be 0, 2 or 3. Then we have this vibrational degrees of freedom. These vibrational degrees of freedom are exhibited only at high temperatures. Only at high temperatures we have this vibrational degrees of freedom. If an object or a gas particle or a gas molecule vibrates in one dimension, then it will have two additional degrees of freedom, one for vibrational potential energy and one for vibrational kinetic energy. So if it vibrates in one dimension, it will have two additional degrees of freedom. You'll have to remember this. Do we understand this?
Yes, sir.
I'll give you 1 minute to note it down. Then we move on to the different types of gases and how many degrees of freedom it can have. When we talk about monatomic gases, we are basically talking about that inert gases, helium, neon, argon, krypton, and so on. Do we understand this? Now they are single atom gases. They do not have a molecule. They are single atom gases. So their number of degrees of freedom are 3. Atoms can just move. They cannot rotate. Atoms can move in all the 3 dimensions. So they have 3 degrees of freedom and all are transitional in nature. Do we understand this?
Yes, sir.
So a monatomic gas will have 3 degrees of freedom. All 3 are translational in nature. You understand this? Yes or no?
Yes, sir.
Now, but once we talk about diatomic gases, for diatomic gases can move in space in the 3 dimension, but at the same time, the molecule can rotate because now it's a molecule. It can rotate also. You can see this is one molecule and this is one molecule. It can also rotate. But if I see this molecule, the moment of inertia about this axis, because the molecule lies on this axis, would be 0. So even it cannot rotate on this axis because the moment of inertia is 0. But it can rotate about the y-axis and the z-axis where it has a considerable moment of inertia, and therefore it will have 5 degrees of freedom. Any gas such as N2, O2, H2 and so on will have 5 degrees of freedom. Translational mode is 3 and rotational mode is 2. Do we understand this?
Yes, sir.
Translational mode, translational freedom is 3, rotational is 0. Here translational is 3 and rotational 2. In monatomic gas, translational 3 and rotational 0. Last but not the least, we come to triatomic gases or polyatomic gases, which are non-linear. I hope you understand the meaning of non-linear.
Yes.
Non-linear gases means H2O and so on. They do not have a linear molecule. You understand the meaning of linear molecule? Linear molecule is like this. So non-linear triatomic gases, if we talk about non-linear triatomic gases, can you now tell me how many degrees of freedom it will have? Mono triatomic non-linear gases, how many degrees of freedom it will have? It will have 6 degrees of freedom. You can see the molecule is here. It can rotate on the x-axis. It will have moment of inertia. The molecule is like this. It is triatomic. You can find the moment of inertia about x-axis. You can find the moment of inertia about the y-axis as well as z-axis. H2O. NH3 and so on. It will have 6 degrees of freedom. Transitional modes are 3 and rotational modes are also 3. Do we understand this? Or this has gone above our head saying bye bye?
Understood, sir.
I'll give you 2 minutes to note it down. Then comes this table and everything that we have learned is given in this table, tabular form. Monatomic gas, helium, neon, argon, krypton, xenon, transitional 3, rotational 0, total 3. Diatomic gases C2H2, 3, 2, 5. Triatomic linear CO2, C2H2, 3, 2, 5. Triatomic non-linear 3, 3, 6. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note it down. Now remember that these degrees of freedom are only at room temperature. At high temperature, not for monatomic gases, they cannot vibrate. But at high temperature, in case of diatomic or polyatomic molecules, the molecules may also vibrate. The molecules may also vibrate, and then they can have vibrational energy coming into the picture. Do we understand this? Yes or no? No, yes.
Yes, sir.
For each degree of vibration, for vibration in one dimension, 2 terms would be added. Yes or no? No, yes.
Yes, sir.
Now, if a diatomic molecule is free to vibrate in one dimension, normally they vibrate in one dimension only, the number of degrees of freedom will become 7. 3 plus 2 plus 2. Do we understand this?
Yes, sir.
A very important fact here about the degrees of freedom in solids. What type of degrees of freedom a solid atom will have? Atom in a solid. How many degrees of freedom atoms or molecules of a solid body will have? They cannot translate, they cannot rotate, they can only vibrate. Ding 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 ding. And for 1 degree of vibration, for one axis of vibration, they will have 2. They can vibrate on all on 3 axes, and therefore their number of degrees of freedom would be 6. Remember this. Do we understand this? Yes or no? No, yes.
Yes, sir.
2 minutes you have. Then we move ahead and we move on to the next heading of this chapter. The next heading of this chapter and the next heading of this chapter is Maxwell's law of equipartition of energy. This is a law. Maxwell's law of equipartition of energy. Maxwell's law of equipartition of energy. This is a law. What does this Maxwell's law of equipartition? Now, every gas, every ideal gas or every gas has this molecules, and these molecules may process a kinetic energy. Now, gas has a number of molecules, it has a number of degrees of freedom. So gas, what it does, as a father, if you have a number of children, you will give your property equally, and that is what the gas does. the total kinetic energy it has, it will equally distribute it among every particle in every degree of freedom, and the kinetic energy per mole per degree or per molecule per degree of freedom is given by this half kT. So energy given per molecule per degree of freedom, kinetic energy per mole per molecule per degree of freedom, energy per molecule per degree of freedom is half kT. This law is known as law of equipartition of kinetic energy or energy. So from here you can write energy per molecule will be half F into kT, or total kinetic energy of the gas molecules will be N by 2 FKT. Do we understand what I have said here? Yes or no?
Yes, sir.
The same thing can be said in terms of energy per mole per degree of freedom. Energy per mole per degree of freedom will be half RT. As I told you, when number of moles come, R will come. So energy per mole will become half FRT, and total energy becomes N by 2 FRT. These are the two very important results that you must remember. Now, whenever we are talking about the energy in this fashion, we are talking about the kinetic energy of the particles in this fashion. Do we understand this? We're
Yes,
not
sir.
talking about the potential energy, kinetic energy partition. I'll give you 2 minutes to note it down. Now, at this point in time, let me introduce the term internal energy of a gas. Now, this internal energy of the gas is normally denoted by the letter U. And you can see that same U I have used for the kinetic energy or the energy of the gas. Now, whenever we talk about internal energy of the gas, this internal energy of the gas can be of three types. And we already have seen the three types. One is the potential energy. Do we understand this?
Yes, sir.
The other one is the kinetic energy. The third one is the vibrational energy. Do we understand this?
Yes, sir.
Vibrational energy. I'm just putting vibrational energy in a different way. Now, this potential energy, it comes, this potential energy comes because of intermolecular attraction or intermolecular interaction. Interaction between molecules, and for these ideal gases, this potential energy PE is taken as 0 because we assume that there is no intermolecular attraction between them. Do we understand this? Yes or no?
Yes, sir.
Now, this kinetic energy can again be divided into two categories. What are those two categories? We already know this. Two types of kinetic energy. What are that two types of kinetic energy?
Translational energy, rotation.
Translational KE and rotational KE. Do we understand it?
Yes, sir.
Now, this vibrational energy that we have written, This will only come at high temperatures. Yes or no?
Yes, sir.
Now at high temperature, when it comes, it again will have two branches inside it. One vibration, it has two. One is known as vibrational potential energy and the other one is known as vibrational kinetic energy. So this is what the internal energy of the gas is. If we neglect the higher temperature and we neglect the potential energy, the total energy of the gas is in the form of kinetic energy of its molecules, whether it is rotational kinetic energy or it may be translational kinetic energy. Do we understand this?
Yes, sir.
Yes or no? No or yes?
Yes, sir.
Everyone understands this?
Yes, sir.
Law of equipartition of energy. Then let me give you this question. Energy of all molecules of a monatomic gas. Pressure P, volume V is 3 by 2 PV. The total translational kinetic energy of all molecules of a diatomic gas at the same pressure and same volume is how much? Remember, here the total energy of all molecules of a monatomic gas is there. Here, the total translational kinetic energy of all molecules of a diatomic gas. Give you 2 minutes to give me the answer for this one. Option B is correct. Monatomic gas only has transitional degrees of freedom, 3 by 2. Total transition kinetic energy. A diatomic gas will also have only 3 degrees of transitional freedom and therefore the answer is this. If they would have asked what is the total energy of diatomic gas, then the total energy of the diatomic gas will become 5 by 2 PV. Yes or no?
Yes, sir.
Because it will have 2 degrees of rotational freedom as well. Do we understand this?
Yes, sir.
This is the next one. CO2 is a triatomic gas. Mean kinetic energy of 1 gram gas. 1 gram gas? What do you mean by 1 gram gas? 1 gram of the gas. 1 gram of the gas.
Yes. चाहिए जो-
Yes, we got the answer for this one. Shall I do it?
Option B, sir. 5 by 88 in KT.
Option B, sir, 5 by 88. That is correct. 5 by 88. Everyone got this? Yes or no?
Yes, sir.
Shall I do it or we have understood this? Okay, I think we have done this. So let me move on to this question. A light container having a diatomic gas enclosed with in is moving with a velocity v. Mass of the gas is capital M and the number of moles is N. There are two questions. Please give me the answer first. Yes.
Kinetic energy with respect to center of mass is 3 by 2 n into Avogadro number by mass into V square.
Kinetic energy with respect to the center of mass of the system is 5 by 2 nRT. Number of degrees of freedom is 5. 3 transitional, 2 rotational. It's also rotating. N is the number of moles, R is the universal gas constant, and T is the temperature. Kinetic energy of the gas with respect to ground will be equal to half m into V square plus 5 by 2 nRT. Do we understand this? Total energy here. I've given you this formula. Total energy n by 2 FRT. Yes or no? No, yes.
Yes, sir.
That is what I have used here. Do we understand this? Yes or no? No, yes. Huh? Or this has gone above our head saying bye bye. Bye bye, I am going bye bye. We understand this?
Yes, sir.
This is the next question. Two gases are mixed. Temperature T1, T2. There is no loss of energy. If the masses of the molecules of the two gases are M1 and M2, and the number of their molecules are N1 and N2, find the temperature of the mixture. We had done something in calorimetry where we had mixed two mixture. Here two gases are mixed. I'll give you 2 minutes to think about the question.
Done, sir.
This is CV. We also need to understand the next term, which is CP. And what would be CP? Everything remains same. We just have to change from constant
Press.
volume to constant pressure. We understand this, yes or no?
Sir.
So from constant volume to constant pressure, if we change, we'll have two types of specific heat. One will be specific heat per gram, the other would be specific heat per mole, and specific heat per mole is what we have to understand CP. So I can write heat given to the gas at constant pressure will be equal to NCP delta T. Do we understand this, or this has gone above our head saying bye bye? Yes or no, no or yes?
We understood, sir.
Okay, I'll give you 2 minutes to note it down. Well, we have to now understand one formula which is known as the Mayer's formula. And what is the Mayer's formula? Mayer's formula. Mayer's formula is very simple. Cp minus Cv is equal to R. That formula is known as Mayer's formula. Now, Cp minus Cv is R. That is one formula that you have to remember. Also, you have to understand that the total internal energy of the gas was written as F by 2 nRT. That can also be written as NCV into T. That means your CV becomes F by 2R. The Mayer's formula is only this much. What I am giving you is apart from the Mayer's formula, what is the relation between Cp and the degrees of freedom. CV becomes F by 2R. So your Cp becomes F by 2 plus 1 times R. Do we understand this?
Yes, sir.
Also, one more thing that you have to remember, Cp by Cv is something which is known as gamma, the coefficient of the two specific heats. Gamma. Cp by Cv is equal to gamma. So these are some of the relations that you must remember. So if you put the values here, you can say gamma will become Cp by Cv. If you just put the values, you will get the value of gamma as 1 by 2 by F. 1 by 2 by F. I'll give you 1 minute to note it down. This was the table that we had already made. Yes or no? We can now add some uh, more terms in this. This is the degrees of freedom that we are talking about, right? The degrees of freedom is equal to 3. Yes or no?
Yes, sir.
So you can write the kinetic energy will be 3 by 2 nRT. Yes or no?
Yes, sir.
This will be the transitional kinetic energy. The rotational kinetic energy would be 0. Total kinetic energy or total energy will be 3 by 2 nRT. Do we understand this?
Yes, sir.
Here also you can add total transitional kinetic energy is 3 by 2 nRT. Rotational kinetic energy will be 2 by 2 nRT. Total energy will be 5 by 2 nRT. This would be same as this. This would be same. This would be 3 by 2 nRT. This would be 6 by 2 nRT. Do we understand this, or this has gone above our head saying bye bye?
Understood, sir.
Now, coming back, you can now add a column which says CV. You can add one more column which says CP, and you can add one more column which says gamma. Do we understand this?
Yes, sir.
This will be 3 by 2R, this will be 5 by 2R, and gamma will be 5 by 3. Yes or no?
Yes, sir.
This will be 5 by 2R, this will be 7 by 2R, and this will be 5 by 7. 5 by 2R, 7 by 2R. Why I've written 5 by 7? It is 7 by 5. 7 by 5. 7 by 5. Here it will be 3 3R, this will be 4R, and this will be 4 by 3. Yes or no? Do we understand this?
Yes, sir.
I'll give you 2 minutes to complete this table. This table has everything that we have discussed till now. CV of the mixture, CP of the mixture, and gamma for the mixture. Note it down. Let us move ahead and move on to one more thing, and then probably we can move on to some questions. You now state variables. Now, whenever we talk about a gas, the state of the gas means by the state of the gas or the state of the system, we mean what that gas can do, what properties that gas have at that particular point. It is similar to coordinates of a point. If a point is here, you can say that the coordinates are x, y, and z. When the point goes here, the position changes. You can call it as x1, x2, y, x1, y, x2, y2, and z2. Similarly, state variables are the terms that tells us the property or state of the gas. State variables define the state of a gas. What are the state variables of a gas? T, P, V, N, U. U means internal energy. All these are state variables of a gas. They only depend on the state of the gas and they define the state of the gas. They are known as state variables. Now, the state variables, the value of this state variable does not depend on path. The value of the state variables does not depend on path. So this is something like your conservative forces. If I have a gas at state 1 where the pressure is P1, volume is V1, temperature is T1, number of moles is N, and energy is U1. Why I've written number of moles as N? Because whenever we are going to do any process on a gas, the number of moles will not change. The gas will not go out or gas will not come in. Now if I change by the change the state of this gas by a series of processes, and these processes are known as thermodynamic processes, which are going to come in the next class. All these processes which change the state of a gas are known as thermodynamic process. So I'm going to change the state of this gas from state number 1 to state number 2. Pressure becomes P2, volume becomes V2, temperature becomes T2, number of moles remains same, the energy becomes U2. Internal energy of the gas is a state variable. It does not depend on the path. It does not depend on the path. So when I go from path A, from point A to point B, the change in internal energy from 1 to 2, you can simply find the energy at point 2 and subtract the energy at point 1, and that will give you the change in internal energy. It does not depend on path, so you can write it as F by 2 NR into T2 minus T1. T2 minus T1 can be written as delta T, change in temperature. So you can write the change in internal energy as F by 2 NR delta T, or you can write it as NCV delta T. This change in internal energy does not depend on path, or it does not depend on the process. For any process which happens between point 1 to point 2, the change in internal energy will remain constant. Do we understand this?
Yes, sir.
Okay. Am I audible and visible to all of you?
Yes, sir.
Okay. I'll give you 2 minutes to note it down. Well, then I will wind off today's class here. We have covered a lot of topics. This topic I'll give you time to go back home and go through this. Otherwise, in the next class, if you don't remember it, the entire thing will go to waste. So we will begin the next class from this note that we have done the energy, and we have seen that it is a state variable and change in energy does not depend on path. Are we confident up till here?
Yes, sir.
In the next class, we will move ahead, and I'll see you in the next class. Take care. God bless all of you. Bye bye.
Thank you, sir. Have a nice day.